Hi everyone, welcome to this Agile Machine Learning, a predictive approach to machine learning functionality webinar. My name is Attila Houtkooper. I'm a principal machine learning architect here at Trifork. Before we begin, as you can tell by now, I have a little bit of a sore throat, so that's one. Secondly, I sometimes stutter, which is, I guess, a good demonstration of that. So if you have any audio problems regarding either hanging or coarse sound, it is probably due to me. Having said that, let's begin. What can you expect from this webinar today? Well, first of all, I'm going to do a short introduction to machine learning. I do realize that quite a number of you have already done something with machine learning. So for you, I'll keep it short. And for those that haven't done anything with machine learning, I hope this short introduction will give you enough insight to understand what machine learning is all about. Secondly, I'll talk a little bit about the application areas in which we see machine learning being of huge value. Thirdly, I'll talk about the way that we do machine learning within our software development projects. We call that Agile Machine Learning as the approach to do that. And lastly, I'll be talking about a case which is machine learning at GeriMedica, a client of ours, and I'll show you what sort of the insights were into machine learning that we got from that. So without further ado, let's get into what machine learning is about. First off, in simplest form, machine learning is about taking data, combining that with modeling methods, and then gaining insights. Secondly, I must admit it's quite a simple explanation so far. Secondly, there are two phases. One is the training phase, where you take a lot of example data and data that you want to train on, and you train your model, by which I mean build up a statistic model of what the data is about. And the second phase is the predicting phase, where you take the trained model and feed it previously unseen pieces of data and expect to get insight based on those previously unseen bits of data. So there are three types of methods for machine learning. There's classification, regression, and clustering. We'll be talking about them in detail in a minute. And lastly, the most important part, or that's not true, one of the important parts of machine learning is doing proper data preparation, by which I mean dimensionality reduction, the practice of reducing data to its most informative parts. And secondly, imputation of missing values. If there's a missing value, either replace it with a default value or with an average value, or even removing the dimension entirely or the data point that has the missing value entirely. If you look at how we analyze data, the CRISP model, or cross-industry standard process for data mining model, describes what we're about to do pretty clearly. At the center of this process, of course, is our data. But then if we look to the upper left, we see one of the most important parts of this and of this talk is business understanding. You cannot look at your data in a vacuum and see, oh, well, it's about log data of servers, so that must mean we must use method X or Y. We need to see what our goal is exactly in analyzing the data and what is of value to the business that we're at. So we know what kind of questions to ask. That is, of course, in close relationship to understanding the data itself. What does the data mean? What does the value mean? Etc., etc. The next step is the data preparation, to which I already talked about. It's about dimensionality reduction, but it's also about normalization of data to make sure that our data is distributed in such a way that we get a fair sample of real-world information. The next step is the modeling phase. This is where one of the three methods comes into play. And then the outcome is a trained model which we can then evaluate. You can see what comes out. We can pair that with the business understanding that we had. Are the things that we thought were really important and crucial to the business, is the data actually pointing that out? Or are there parts of the business or the data that we didn't even think was that important, but actually plays a crucial role? Lastly, in deployment, we take our trained model and we actually use it within a real application. And we will be talking to that today as well. So it's a useful model for us to get an understanding how to analyze data. Let's now look at the different types of methods of machine learning that are there. For this, we use a handy graph made by the good people at scikit-learn, which is one of the frameworks I'll be talking about later on as well. And it's actually a roadmap on the different types of machine learning that are there. So we start at the right top at the orangish start circle. And the first step is, if we have less than 50 samples, we need to get more data. Now that is a fair point to make, although what has to be said here is that indeed for most of the problems 50 samples is way too little, but it depends on the complexity of your data and the complexity of the thing that you want to know. If I want to know the average distance between lampposts in a street, then maybe 50 is an okay number. But other cases quickly deteriorate the quality of the 50. So, and especially if we want to use the scikit-learn methods, then we need more data. Anyway, let's assume that we do and move to the next step, which is whether we're predicting a category or not. So predicting a category is about, for example, having a set of photographs and determining whether there's a dog in the photographs. So we can basically split up our set of photos in either photos with dogs or photos without dogs. If we're talking about such a problem or such a question that we want to answer, then the next question is, do we have labeled data? In other words, do we have examples that say specifically, well, this is a set of photos that have dogs in them, and this is a set of photos that do not have dogs in them? If we do, then we're immediately in the classification area. Because now what we want to do is we want to train a model that is able to take a previously unseen photo and say, this is a photo of a dog, or this is not a photo of a dog. There are a bunch of subsequent steps in there, but we're all talking about the classification area that we're working with here. If we do not have labeled data, so we move back in the tree and we're going back to this one, then we are getting into the clustering area, and that is an example of unsupervised learning where we do not have a clear sort of labeling or a clear ground truth of the data that we're talking about. In other words, we are exploring. We are thinking, okay, there must be some structure in our data, and we would like to see what kind of clusters are there. What kind of groups can I divide my data into? And it may actually be that you'll use clustering methods as an intermediate step before classification. For example, if I were to cluster my photos and I would find that there's a cluster and I take a few samples out of that cluster and it turns out that all these photos are about dogs, I might choose to label that entire cluster as being about dogs. And thus we have our labeled data and can now do the classification thing that we wanted to do. If we move back further still, and it turns out we weren't really predicting a category, but we were predicting an amount, a quantity, that an example of that would be to predict the housing price a year from now. Before I forget, I put some time into these slides, so let me get some examples out of the way before I forget to do that. This is a visual approximation of a classification problem. You have a set of data points, and you're able to basically train the method to say, well, the things on the top left there are red circles, and the things on the bottom right there are green pluses. And with the clustering, we get a collection of data points, we're basically able to say, well, these are the clusters that are in play. Anyway, getting back to my point, if we're predicting the housing price a year from now, then what we're doing is regression. That may sound like you're going back, but actually you're going forward. So what does that mean? Well, the picture there is quite clear as well. You've got historic data, which is on the x-axis, which says, well, at this point in time, and then y is about the price. So in this case, the price has gone up over time. And if we want to predict something that is in the future, so further to the right from the things we've seen so far, then we can predict it must be somewhere in the top right corner based on the information that we have so far. Now, this is, of course, a very simplified view. There are complicating factors such as seasonality of prices and all kinds of influences that make a regression model not the holy grail for everything that you want. And there are different kinds of regression models. But in principle, this is what you're doing at that time. Now, if we step back again and we say we weren't really predicting a quantity, we just were looking at the data, then one of the things that you want to do is, again, an unsupervised method, which is dimensionality reduction. And here we are trying to reduce the amount of attributes, the amount of things that we know about a data point to a lower number. And there are some solid reasons to be able to do that, to want to do that. One reason is it makes the data simpler. So it makes it more insightful what is unique about a data point and what is not. And secondly, this actually helps you to create better data, because if we have two attributes that are actually representation of the same physical thing, such as if I were to look at my houses and I would have GPS location as well as an address field, then basically that both of those things represent the same thing, namely where the house is at. So it's very likely that these things are basically very similar in the meaning that they hold, and we would want to get rid of one of them. And why is that? It is because if we don't, then we basically are saying to the model that is learning, we're saying that the location of the house is twice as important as any other attribute. And that is most likely not what we want to say, because it just so happens to be that we both have the GPS coordinate and the address in there. So for those kinds of operations, you want to do dimensionality reduction, and one of the sort of key methods in that is principal component analysis, which helps you to statistically look at what are the most discerning attributes of the items in my data set. So what are some of the application areas that we see in our daily life here at Trifork? One of them is optimization of workflows. A great example of that is support desk software, where a client will be asked any number of questions, and maybe it's like 13 questions, but an expert is able to say after 3 questions, I'm just going to skip right to question 12, because I know that the rest doesn't really matter for the solution that I have in mind that's probably going to fit this customer best. So in other words, I take a shortcut. Now this is all kinds of advantages, and that's what make the experts the expert. But if you have seasonality in your service desk people, then you'll have a time where it's really busy, and you have a lot of very new employees that don't have that expert level yet. So if we're able to build that into the system, that is going to increase the quality of the work that those new people do. So secondly, machine learning is used to detect anomalies. So one of the practical examples of that is predictive maintenance. Imagine you have a trailer truck that drives, and it needs to go to the south of Spain, And in the middle of Spain, right in the summer, a coolant trailer breaks down. A coolant trailer is a trailer that has a coolant system on board and likely fresh produce or ice cream or something that doesn't stand heat all too well. And having that break down next to the highway in the middle of the summer will likely mean that the contents of that trailer are going to be worthless. What if we were able to actually analyze the data that comes off of these trailers, such as air pressure, braking fluid, tires, and the thickness and the depth of the grooves, and everything, and then we're able to say the evening before it crosses the middle of Spain, hey, you're now driving next, or you're now going past a garage. Why don't you have your air pressure checked? That would mean minimum downtime, minimum delay, and it would save the contents of that trailer. So another nice example. The second example within detecting anomalies, of course, fraud detection, a more popular example, and that goes into can we detect whether an event lies outside of what we expected. If all of a sudden I'm making a withdrawal, or in that case, my bank card is used to make a withdrawal halfway across the world, that lies sort of outside of the norm, and that may be a reason to do an extra checkup. The third area where we see machine learning being used is in the legal area. One example of that is a comparison of contracts, large bulks of contracts within the legal sector that sort of deviate from a standard contract. And then if we're able to extract standard information and identify the deviations, we can make a summary that is a lot easier to read than going through all of the contracts and figuring out what their outliers are, or what their exemptions are to the standard. Lastly, we've been using machine learning in publishing, where we were able to cluster texts, news articles, and be able to identify opinion makers within a commenting system. And if we look at tooling, then it's very much Python oriented. At the beginning, there is a library called NumPy, which allows you to do powerful mathematical operations on your data. Pandas is a tool that allows you to introspect and to easily make changes to your data. For instance, when you're working with unknown values, missing values rather. Then you get to scikit-learn, which contains some more basic machine learning functions that allow you to do principal component analysis, clustering, these kinds of things. And then once that sort of analysis is done, then you get to the Keras and the TensorFlow libraries that allow you to build complex neural network machine learning methods that are very powerful for very complex tasks. So if we look at the difference between developing an application with machine learning features and sort of your standard day-of-the-mill, say day-of-the-mill, that's awesome, application, then we can see that in your regular application development, there are very clear expectations. The product owner writes a story saying, listen, I expect a button on this page, and when the user clicks the button, it should go there, and for other users, it should do something different, etc. It's all very deterministic. And that is very good because that conveys very well to developers, and developers are build the button, and then the testers know how to deal with that. And this sort of system works because everybody's been trained to work in this kind of in this kind of a way. Now, if we compare that, if we square that off to machine learning development, then things become a lot more fuzzy. There are a lot less clear expectations. Are we building functionality, or are we just analyzing the data? And how do we measure successfulness? How do we say this feature does exactly what I expect it to do? When a lot comes down to a statistical model, which depends on the complexity of the data, how far you can oversee the impact of that feature. So it bears some emphasis that we make sure that we know what we're doing and we know what we want. So this is why we're sort of taking this approach. We build up a methodology called Agile Machine Learning, a proven process using Agile methods. We start in a very small way, allowing us to do quick iterations that deliver real working functionality, and expand on them later on as we need to. And that allows us to roll out fast. In other words, you don't have to wait for 6 months until you have a feature, but you build a feature in a regular sprint, and you see whether it works for your users or not, as you're used to. So how does it look exactly? We start off, when we do a project, we start off with a number of workshops where we, first of all, do a workshop with domain experts. So experts in the application, experts in terms of what the customer wants or what they expect, these kinds of people. And what we get from that, I'll dive into later before I start saying everything on this slide. Anyway, secondly, there's a data sourcing workshop. So now that we know what we want, we now want to know what do we actually have in terms of data sources. After that, we do iterative implementation, where we polish the specifications, build it, and deploy it, and we bring it directly to production to be able to gather feedback and to see whether what we've built actually works in real life. So the domain expert workshop, it's the people that understand the core of the business problem. So this, if we reflect back on the CRISP model I showed you way in the beginning, this is what is understanding the business domain is about. Here's where we get the really bright people, they do this, or the experts that have so many years of experience, they know how to deal with this or that situation. And then we ask the question, so what do you want to sort of solve, optimize, or provide? Do you need to reduce user delays? Is that sort of a big issue? Do you want to create better decisions so that your most junior employee is still able to deliver top of the line service to any customer? Or do you want just faster decisions, just quicker decisions that say, well, never mind about the rest, we just want to do this, and that's going to save us effort and energy. And lastly, we need to look at how it will look in the application. If we just stop short of this part, then all it is that we're doing is data analysis. We're just figuring out what would be nice, what would be a good idea, and we don't believe that that's going to deliver a lot of real value in the end. We need this extra step that says, okay, now if you know that, or if you're able to provide that, how will I make sure that my users will actually use this insight and go forward? Now, after we've set up these what we call questions, sort of the optimizations and the things you would want the system to provide you with, then we need to know what kind of data is there to provide the answers for that. Do we have that all internally? That could be a database, historic tables, or log data. Or do we need external sources such as weather or traffic or any of these kinds of things? During that workshop, we also determine what kind of machine learning methods we want to apply. And the reason for that is that it might mean that we actually need a ground truth. we need to know whether, suppose that would be a business problem, the pictures of a dog thing. Perhaps we do need a minimum set of pictures that we are certain of that those are dogs, and if we don't, then we cannot basically start to build a solution. So that would be considered part of how do we source that ground truth, basically. And then another part which is important is how do we measure success? If we have all this, if the data is there, what does it mean to be right? What does it mean to be wrong? How much time do we absolutely have to be right? Or can we afford it to be every once in a while be wrong? And we put a cost on that so that we're able to train our software in an optimum way, taking those costs into account, as well as the benefits for getting it right. Then we go into iterative development. Now this is not much different from your average agile project. So we got 2 to 3 weeks iterations in which we refine the questions to be analyzed. We refine how they will be represented as functionality, and we refine as to what part of the data do we realistically need. Now we do this merely as a practical measure because getting the data is often a little bit more work to actually disclose it and make it available, etc., etc. So we specify that as well. And then we choose, of course, the machine learning method is a combination or one of them enough. And then we implement and we show it, etc. So then we get to the last step, which is direct to production. So why do we want to do that? Well, we need to gather feedback. We've built the functionality. We are convinced that the users will like it, but we need to know whether the users will get that functionality at the right time and whether they're able to improve basically on what they did before. So we need to know about usage, whether the users actually find it satisfactory, what the functionality is showing them, and then showing what the actual outcome is. Is it actually improving? Are there actually satisfied customers at the end of the line that say, well, that was really quick. That must have been an expert. Well, it was a junior, for example. And then using that feedback, we can do continuous improvement on a model where we feed back this feedback into an incremental training cycle on the model. Now, onto that, there's different deployment strategies, and there we split between training and predicting, where training is likely to be a very long-running process versus predicting really fast and real time, and where training might happen initially on a laptop using something as simple as Spark MLlib or something else, but it could also be on a cloud situation. And on the predicting side, you would typically build an API, and it may be a streaming data service, and definitely on something that's either cloud or if your data requires it on-premise servers. So let's look now at a case study on applying machine learning. In this case, at GeriMedica. So GeriMedica is a business that develops a platform for electronic medical records for elderly care. And the goal of our project was we wanted to project what the usefulness and the duration of treatments was. So examples of that were high blood pressure symptoms treated in similar situations. What is the total duration and intensity based on reports so far? And another, which labs requests have been made in similar situations. Now, these examples, I don't put them here for nothing. This is actually another example where you really want to be able to understand the business domain in which your data is created. Because why would I want to know whether high blood pressure symptoms were treated? Because it's an optional thing. It might actually be that treating another thing actually causes high blood pressure. and actually treating high blood pressure in that case is stopping the treatment of something that may be far worse. The total duration and intensity is something that is handy for resource allocation and for assurances. And the lab requests is actually something that is there are so many different options when researching or when doing analyses, requesting analyses rather, on blood samples, that you really it's really handy to have something that tells you, well, it may be interesting to also look at these levels in their blood and see what's up with that, because we have examples of people that were actually that would have been useful for. So the approach that we took here is we used two different techniques. We used doc2vec, which I'll talk a little bit about in a minute, to basically turn text into vectors. And we use neural networks both for regression and classification of the vectors we've created. So what kind of data sources did we have? So first of all, it's an electronic medical record, and we see we had about 2 million individual reports of doctor-patient interactions, and we had some medical history, some episodes, warnings, forms, measuring instruments, and some more categorical data. And you see that there's a lot of different kinds of data in there. There's categorical data, numerical data, and there's textual data. So we need some way to model that into a single form that we can do something with. Now, next to that, this entire medical record was stored in a timeline of events. That was done using Axon framework, which is a framework developed by another Trifork subsidiary. And that framework actually is an event store. So it just records changes within a certain context. So it's another way to do analysis on historical data, or provides it rather. So what was the goal that we had? We wanted to do recommendations based on similar data. So that's an unsupervised method. So we basically wanted to cluster our patient records and say, well, this person looks a bit like this other person, and this other person had their high blood pressure treated at this point. So that might be a useful thing to do. And secondly, we wanted to classify new data. So, for example, we wanted to know what the likelihood was that a certain patient had a certain disease, but we needed to be sure that we had a balanced data set. So there had to be an equal number of examples per label. So as soon as we were able to classify these individual reports, then on an abstract level, we ended up in this kind of a situation where we have timelines for each individual patient with different kinds of events. Maybe there was a blood test, and then the blood test outcome came, but then they had a stomach flu or something like that. And using that, we're then able to say, well, we now have a current patient that has this sort of a history. What sort of choice was made for similar patients? And we can look at historic cases, and we see that we actually have in this case, we have a few, and we can say something like, well, in 2/3 of the cases we did so, or we did something else. But to get there, we need to turn our data source into input data. And what does that mean? Input data needs to be a fixed size feature vectors. That is the language in which we talk to our machine learning algorithms. We provide them with a series of data points, which are always numbers, and these need to be the same size for every single data point that we give. And for numerical data, that doesn't require much work. But for categorical data, it's a little bit of work, because there we need to say, okay, so this report is about hypertension. So that means we add a dimension saying, well, this dimension says whether the report was about hypertension. Okay, so that's also relatively simple. Then the next is more complex data like text. Other examples of complex data which are more densely populated with information are audio and image data. And for text, we need to vectorize these documents so that we're able to see what are similar documents. And we can either do that with sort of IDF or doc2vec. And I'm going to talk a little bit about doc2vec in a minute. So once we have done that, we've vectorized everything that wasn't a vector, and we've combined that in one big string of numbers. Then what we need to do is we need to make sure that data is now normally distributed across all of these different attributes. And why is that? It's because these machine learning methods all assume a normal distribution on your data. And if you don't have that, then you may get some outcomes, but they're not going to be reliable, basically because these machine learning methods assume that you get a realistic sample that is well weighted and represents reality in that. And if you don't provide that, then you're going to get results that may work for some of your test data, but it will definitely not get great results in real life. Once we have the numerical data, of course, we need to impute missing values on that. That is part of this pre-processing step from data source to input data. Next, let's talk a little bit about turning texts into vectors. So before I mentioned doc2vec, and this slide is called word2vec, and the reason why I use them interchangeably, because doc2vec is basically a superset of word2vec, and word2vec is a nice example to explain, and then it'll be a logical conclusion how doc2vec actually works. So word2vec creates vectors of text, and that means that it does it in such a way that it models the relationships between words. And to be able to see that, I took an image from the TensorFlow website, which explains this algorithm really well. It basically shows you that relationships between words are modeled in a similar way. So, for example, in the first image on the left side, you see that the relationship between king and queen and men and women is actually a similar relationship. And to be able to get that from just plain text is a really powerful tool, because it basically means that we can take very implicit information and actually get the relationships from that. And you have to imagine that doctors type about at the same quality at which they write. So it's all populated with shorthand and barely any grammatical structure in the sentences. To be able to use such a method and to see that it actually has a value makes it a very powerful tool. So similarly to word2vec, doc2vec then allows you to say, well, this report is actually as similar relationship to the report that follows it as another report. So moving on, let's look at an example. So one of the ways we wanted to test whether this was of any use to us is we said, okay, we want to see what is lisinopril. Well, we had to look that up. Lucky there's a website called drugs.com which does exactly what you expect, namely tell you about information on medication. And it turns out lisinopril is a high blood pressure drug that is an ACE inhibitor. So it uses that to decrease high blood pressure. So we wanted to know what are medications that are similar to lisinopril, because if we know that, then we can basically say, well, any report that's about lisinopril or any of its equivalents, we can label that as being about high blood pressure, which is again useful for classification problem that we had. So we asked an expert, and he gave us a list of 9 of these medications, and we started to build a bit of script that would label everything based on that list of 9 things, etc., etc. But then we said, okay, now let's ask Word2Vec what its things. So Word2Vec came back and said, well, I've got these 10. They are sort of alike. So at the top is something called enalapril, and that's about exactly the same thing. So it also treats hypertension, and it's also an ACE inhibitor. In fact, if you move down the list and things that are less similar, we encounter stuff like bisoprolol, which is also used to treat hypertension, but then being a beta blocker, so treating it in a slightly different way. And the same thing for nifedipine, which also treats high blood pressure, but then by being something called a calcium channel blocker. Now, what does that tell us? Now, first of all, the expert said, "Oh, that's right, I forgot one." So that already was sort of a moment where you would say, "Well, it really makes sense to look at the data and use as much as we can from that." Secondly, what this tells us is that we can, by looking at how a word is used, we can see what are similar words within our data set, and that allows us to do clustering in a very meaningful way. But it also allows us in the end to label these relationships and actually infer for the kinds of events that have happened. So, in conclusion, machine learning is often a combined approach of techniques to simplify your data and discover clusters of data. It's not a one-size-fits-all approach. There isn't distrust anyone who will tell you, oh, you need to use recurrent neural networks because they are the absolute best. Because it really depends on the kind of data, the kind of problem that you want to solve with that data, to know what kind of method makes the most sense. Often the simplest method is the method that is fastest and is most reliable and understandable, and that is definitely not a one-size-fits-all approach. So secondly, you then need to know your business context of your data. You need to know what is of value to your business or the business that you're working for, because otherwise you're focusing on answering questions that nobody really needs the answer to. Thirdly, what this allows you to do is turning implicit expert skill into explicitly available functionality to anyone. By which I mean, if an expert knows what to do after question 3, then if we can make that into an explicit feature that at question 3 says, well, we are now quite certain that you need to skip to question 12, then we've created a very powerful way of encapsulating that expert knowledge into the system. And lastly, Agile Machine Learning, which I talked about a bit, is the approach of building real functionality within real applications using machine learning. So far, this webinar. Now, I want to talk a little bit about who is Trifork and tell you a little bit about the training that is coming up in next year. So Trifork Global was founded in 1996. We've got 400 software experts in 22 different businesses across basically the Western world and South America. And we basically are good at three things. We do expert projects with innovative technology. We sometimes spin off a product, so there's a very high entrepreneurial spirit within the offices. And thirdly, we share knowledge as much as we can through things like this webinar, as well as organizing go-to conferences around the world and organizing trainings. At Trifork Amsterdam specifically, we have high expertise in open source technologies in Java. We have three focus areas, which are microservices architecture and tooling, Agile Machine Learning, which was what this webinar was about, and customer innovation projects. And yeah, some of the spin-offs that we've created so far are learning solutions, a product company focused around a teaching software for taking exams, and Exonic, which is all about the Exon framework and providing services and platforms around that. So the training that's coming up is next year. It's a 2-day training on hands-on machine learning from February 22 to the 23rd. And it basically allows you to dig really deeper into the topics that we've addressed in this webinar. You get some hands-on experience, some of the methods that we've been talking so far, and we're there with experts that will tell you how we do this in real life, address supervised and unsupervised learning, and use the libraries I was talking about before. If you're interested in all that, please go to Academy, and if you want to directly mail and get some rebate, use the code word webinar. Now, if you ever want to talk to me and mail me, you can reach me at aho@trifork.com, which indeed says aho. Okay. If you want to learn more about machine learning at Trifork, go to trifork.com/machine-learning. Thank you very much.